Good day everyone, so we're here to answer 3 physics problems in Universal Physics book in chapter 10, Dynamics of Rotational Motion. So let's get started. For problem number 1, rigid body rotation about a moving object. So a string is wrapped several times around the rim of a small hoop with radius 8 centimeters and mass 0.18 kilograms. The free end of the string is held in place and the hoop is released from rest. After the hoop has descended 75 centimeters, calculate the angular speed of rotating hoop and the speed of its center. So at this point, since it in the problem it is said that the free end of the string is held in place, so it should not be moving, so the kinetic energy here is 0. While for this one, okay, since it's rotating, and I think there is a force acting upon it, which is gravity. So gravity pulls the hoop down, and it goes down due to the gravitational force. So here, the formula, as I said, kinetic energy is 0, and then for potential energy, since there is potential energy, which is gravity, so there, and then we're gonna use the kinetic energy, translational kinetic energy, which is 1/2 mv squared, the rotational kinetic energy, which is 1/2 I omega squared. So we're gonna add them with like kinetic energy plus trans plus kinetic energy, the rotational, which is equal to the potential energy. And since the axis is perpendicular to the center of the spin, our I will be equal to mr squared. And then we all know that to calculate V, we need it is omega times r. So we're gonna add this one and this one, substitute the value of I here. So we all know that this big M and the small m is just the same, so we're just gonna cancel that. So here we're gonna add this side. On this side, if we're gonna add them, we're going to have 1. So m omega squared times r squared is equal to mgs. This is our potential energy. So these two m's will be cancelled, and then we're going to be left with omega squared times r squared is equal to gs. And then we're gonna, since we need to find the angular speed of the rotating hoop, and it is omega, so omega should be left alone. So we're gonna divide it by r squared, divide both sides by r squared, so there, and then we need to square root, so we're left with omega is equal to square root of gs times over r. So since we have the formula, we're gonna substitute it. Our given is 8.8 centimeters. We're gonna convert it into meters, and also this one. So we're just gonna substitute 9.8, since our g is 9.8 meters per second, times s, which is 0.75 meters, over r, which is 0.08 meters, and we're gonna have an angular speed of 33.9 rad per second. And also we need to calculate the speed of its center. So our formula is V is equal to omega times r. We have our omega, which is 33.9 rad per second, times r, which is 0.08 meters. We're gonna have 2.71 meters. Okay, so for problem number 2, it is about conservation of angular momentum. Spinning figure. The outstretched hands and arms of a figure skater preparing for a spin can be considered a slender rod pivoting about an axis through its center. When the skater's hands and arms are brought in and wrapped around his body to execute the spin, the hands and arms can be considered a thin-walled hollow cylinder. His arms have a combined mass of 7.0 kg. When outstretched, they span 1.7 meters. When wrapped, they form a cylinder of radius 24 centimeters. The moment of inertia about the rotation of axis of the remainder of his body is constant and equal to 0.40 kg meters squared. If his original angular speed is 0.30 rev per second, what is his final angular speed? So in this problem, we need to find the final angular speed. So these are the given in the problem. So the moment of inertia of the rod about the axis passing through the center is given by 1/12 times m r squared, wherein m is mass and r is this one, the length of the arms. Okay. And then for the moment of inertia in the hollow cylinder, it is I is equal to m times r squared also, wherein m is mass and r is the radius. Okay, so the angular momentum, as we all know, is the product of the moment of inertia and the angular velocity, which is I omega. And then we need the total initial, we need to use the total initial moment of inertia. So it is I, which is I final is equal to I plus I initial. Okay, so we're going to substitute now the values. We're going to look for I initial. So 1/12 times m times r squared, the initial r, plus the constant. So plug in the values. You're going to get 2.0858 kg meters squared. And for the final, we're going to use mr squared plus the constant. Plug in the values. We're going to have 0.8032 kg meters squared. So using the law of conservation of angular momentum, the final angular momentum is equal to the initial angular momentum, which is L initial is equal to F initial. And then we're just going to substitute this one since we're looking for the final angular speed. So we're just going to rearrange this equation to find the final angular velocity. So plug in the values that we have, and then we're going to get 0.7791 rev per second. So we need to convert rev to rad. So here the answer is 4.952 rad per second. I think we don't need to convert it also. So we have this answer, a final answer, 0.7791 rev per second. So for problem number 3, rolling stones. A solid uniform spherical boulder starts from rest and rolls down a 50-meter high hill as shown in the figure. The top half of the hill is rough enough to cause a boulder to roll without slipping, but the lower half is covered with ice and there is no friction. What is the translational speed of the boulder when it reaches the bottom of the hill? So for this problem, we need to find the translational speed of the boulder when it reaches the bottom of the hill. So the rough and smooth surfaces of the hill are shown in the figure. This one's rough, and this one's rough. So the height of the rough surface is 25 meters, and the height of the smooth surface is also 25 meters, since its total height is 50 meters. So we're gonna think that it's just the half of since half is rough and half is smooth. Okay, so the energy possessed by the body in motion is the kinetic energy. So we need to find the translational kinetic energy, and the formula for that is 1/2 mv squared, wherein this is translational energy, this is the mass, and this is the velocity of the body. So for the rotational kinetic, it is 1/2 I omega squared. So using the law of conservation of energy, we can use it to convert the potential energy that was converted into translational and rotational kinetic energy. So this is the formula: KE plus KF is equal to potential energy. So then we're just gonna substitute this formula to this one here, and our potential energy formula is mgh. So okay, for the spherical boulder, since it is a solid sphere, the moment of inertia is 2/5 m times r squared, wherein okay, so the relation between the translational and the rotational kinetic energy will be this one: omega is equal to v over r. So this the formula that we have earlier, we're just gonna plug in I, and then we're also gonna plug in omega. So this will be our formula now, and then after that we then substitute I. When we substitute I, it will become this one, and then add this one, cancel. We're going to have 1/2 mv squared is equal to 5/7 mg squared. So when the sphere travels through smooth surface, that's for the rough surface, it's the gravitational potential will be converted into translational motion, which wherein it is KE is equal to PE, or kinetic is equal to potential. So the kinetic energy on the smooth surface is KE is equal to 1/2 mv squared, wherein V is the velocity of the smooth surface. So we're just going to substitute 1/2 mv squared, and then we are going to substitute also potential energy in the equation. So it will be 1/2 is equal to mgh, and then for the total kinetic energy of the spherical boulder at the bottom of the hill, it is KE, the total KE, kinetic energy, plus the translational, plus this one, VS. So the total kinetic energy for the spherical boulder is 1/2 mv squared also. Then here, just plug in. We're in, okay, also in the total kinetic energy, it is the VT is the total translational velocity at the bottom of the hill. So just substitute everything. Then we're going to have this one. V is equal to square root of 24/7 G times H. And then just gonna plug in the given values, and that's it. We have a value of 29 meters per second. That's it. Thanks for watching.